Okay, we'll go ahead and finish up section 11.8, which is power series. So I have three more examples I was going to show you here. Suppose that we have the summation as n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, so we're going to use the ratio test with this. And again, for a lot of these problems in this section, they're going to use the ratio test. Okay. So we have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. A sub n plus 1, when I replace the n's with n plus 1's there, I got negative 1 to the n plus 1 times x to the 2n plus 1, that's 2n plus 2, plus 1 is 2n plus 3, divided by 2 times n plus 1 is 2n plus 2, plus 1 is 2n plus 3 factorial. Okay, and then we're going to divide that by a sub n, or we're going to multiply it by the reciprocal of the sequence there. So I got 2n plus 1 factorial divided by negative 1 to the n times x to the 2n plus 1. Okay, and let's simplify that. So we got the negative 1 to the n plus 1 and the negative 1 to the n. I'm taking the absolute value of those numbers. So that's going to be 1. Those are gone. X to the 2n plus 3, that's the same as x to the 2n times x cubed. And I'm dividing that by x to the 2n times x. The x to the 2n's cancel. So I'm looking at x cubed divided by x, that's x squared up top. And then 2n plus 1 factorial divided by 2n plus 3 factorial. Well, 2n plus 3 factorial, that's the same as 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, right? And so the 2n plus 1 factorial will cancel with 2n plus 1 factorial in the denominator, and that's going to leave me with just the first two terms, which is 2n plus 3 times 2n plus 2. Again, the 2n plus 1 factorial, which would be the rest of those terms, that's going to cancel with the 1 up top. N is approaching infinity. So the denominator is growing without a bound as the numerator just sits at x squared. X squared is a constant, right? Because the limit is in terms of n. So that's going to be 0. Okay. X can be any real number, in other words. Okay. So let's see. So yeah, any time that you're getting a value that's less than 1, you got a convergent series. So x can be anything here. We got 0. The radius is infinity, and the interval then would be negative infinity to infinity. Okay. By the way, this series is a really important series. We're going to see that in section 11.10. This is actually one way to define sine x. Right there. Okay. We're going to look at what's called Taylor and Maclaurin series. That's in section 11.10. Okay, and it's representing functions as power series expansions. Okay, so and the domain of the sine function is all real numbers, right? I can let x be anything. So that's another way to look at it. Let's try this example next. We got the summation as n equals 0 to infinity of negative 2 to the n times x minus 1 to the n divided by the square root of n plus 1. Okay, I'm going to start by using the ratio test with that. And we need to know all the x values that are going to make this converge, right? So let's see, a sub n plus 1 means I got negative 2 to the n plus 1 times x minus 1 to the n plus 1 divided by the square root of n plus 1 plus 1, that's the square root of n plus 2. Okay, and then I'm going to multiply this by the reciprocal of this sequence. So that'd be, when I flip that, I'm going to have times the square root of n plus 1 divided by negative 2 to the n times x minus 1 to the n. Okay, negative 2 to the n plus 1, that's the same as negative 2 to the n times negative 2. I got a negative 2 to the n up there and a negative 2 to the n down there. Those are gone. And so I got negative 2. The absolute value of negative 2 is 2. Okay? And then with the x terms, so x plus 1 to the n plus 1, that's the same as x minus 1 to the n plus 1. That's the same as x minus 1 to the n times x minus 1. I have an x minus 1 to the n down under, so I'll be able to cancel those. And I've got another x minus 1 term left over. Now, I need to keep the absolute value bars around the x minus 1 because x can be anything. And then I'm multiplying this by the square root of n plus 1 divided by the square root of n plus 2. I'm going to go ahead and get a single radical out of that. Now I can lose the absolute value bars around that part because n is already a non-negative number. Okay? The limit as n approaches infinity of the square root of n plus 1 over n plus 2, that'd be 1. Okay? And there's a constant, 2 times the absolute value of x minus 1. That's the value of this limit that I see. Okay, so I need to know when that's less than 1 to know when that's absolutely convergent. Okay, so I go ahead and set 2 times x minus 1 to be less than 1, and I'm solving for x divided by 2. And the absolute value of x minus 1 less than 1/2, that means that x minus 1 is going to be less than 1/2 but bigger than negative 1/2. So then if I add 1 throughout the 3 parts there, negative 1/2 plus 1 is 1/2. 1/2 plus 1 is 3/2. X minus 1 plus 1, that'd be x in the middle. Okay? So right here so far is the interval that I've got. I can know the radius. I got a radius of 1/2, right? Because the interval length is 1 unit. And the radius is always half of the interval length. Okay? Now, make sure that you check the endpoints. Make sure that you check the endpoints. Make sure that you check the endpoints. Okay? The reason why I'm saying that is because I have students that don't check the endpoints, and then they lose points for the problems like this. Okay? You have to check the endpoints, right? Because the ratio test is only convergent if when you're less than 1, right? And it's divergent for when you're bigger than 1. It's inconclusive when you're equal to 1. Okay? So let's see what's happening when x is 1/2 and when x is 3/2. Okay, so if x is 1/2, and I plug that into my series here, 1/2 minus 1, that's negative 1/2 to the n. So I'm looking at negative 2 to the n divided by negative 2 to the n. Those are gone. Okay, and I got 1 then up top. Okay, so I'm looking at the summation as n equals 0 to infinity of 1 divided by the square root of n plus 1. There's a couple of different options that you could take here. So I chose to use the integral test. I'll mention another option after we're done looking at this. But let's see, I got the integral going from 0 to infinity of 1 divided by x plus 1 dx. Okay, well that's the limit as t approaches infinity of the integral going from 0 to t for 1 divided by the square root of x plus 1 dx. Okay, let's see, I could use a u substitution on that, let u be x plus 1, I got this u to the negative 1/2, right? So then if I take the antiderivative of that, I'm looking at u to the 1/2 times 2. Okay, well, u is x plus 1. So I got the limit as t approaches infinity of 2 times the square root of x plus 1, and I'm going from 0 to t. If t is approaching infinity, x plus 1 is going to be approaching infinity. The square root of x plus 1 will be approaching infinity, and when I multiply by 2, I'm still approaching infinity. Okay, so that's divergent. Now, by the way, another way to do this problem would be to just know that it's a p-series. I'm starting the sum at 0. What if I were starting at 1? Okay, this summation is equal to the sum as n equals 1 to infinity of 1 divided by the square root of n. Well, that's a p-series. P is 1/2. Divergent. Done. Okay, so we like this is the longer option to use there. Yeah, what if x is 3/2? Okay, I'm not including the left endpoint. I need to know if I'm going to include 3/2. Well, if x is 3/2, and I plug that in my series here, 3/2 minus 1, that's 1/2. So I'm looking at negative 2 to the n divided by 2 to the n. That's negative 2 divided by 2 to the n is negative 1 to the n. And I'm dividing that by the square root of n plus 1. Okay, so this would be the corresponding series that I get here. By the way, when you're plugging in these numbers, make sure that you simplify. Simplify. You know, because I wouldn't want some, you know, to just leave it as negative 2 to the n times 3/2 minus 1 to the n divided by the square root of n plus 1. Right? And some people will do that. No, simplify the sequence part as far as possible, right? Because we need to know which technique to use to know if it's convergent. Okay, well, there's a negative 1 to the n, so that kind of gives this away that I need to use the alternating series test. We have the limit as n approaches infinity of 1 divided by the square root of n plus 1, that's 0. Okay, and then I need to also show that the terms decrease. Well, is the next term going to be smaller than the previous term? Yeah, so if I replace n with an n plus 1, 1 divided by the square root of n plus 1 plus 1, that's the square root of n plus 2. That is going to be less than the square root of n plus 1, right? Because the denominator on the left is going to be some bigger number. And so the entire fraction on the left is going to be a smaller number than the one on the right. Okay, and this happens for when n is positive, or when n is greater than or equal to 0. Okay, so so in other words, we've got a convergent series here when x is 3/2 by the alternating series test. So the radius is 1/2. We already said that right here. The interval is 1/2 to 3/2, and we're including 3/2. We're not including 1/2 there, right? Because we got a divergent. Okay. Here's one more example. So what if we have the summation as n equals 2 to infinity of x plus 2 to the n times the ln of n divided by n times 3 to the n. Okay, so let's use the ratio test with that. I have the limit as n approaches infinity of x plus 2 to the n plus 1 times the ln of n plus 1 divided by n plus 1 times 3 to the n plus 1. Okay. By the way, the reason why I'm not starting at 0, well, I can't start at 0, right? But the reason why I'm not starting at 1 is the ln of 1 is 0. I'm dividing this by a sub n, so that's the same as multiplying it by the reciprocal. So if I flip the guy on the bottom there, I'm multiplying this by n times 3 to the n divided by x plus 2 to the n times the ln of n. Okay, so what does all this give me? Well, 3 to the n divided by 3 to the n plus 1. 3 to the n plus 1, the same as 3 to the n times 3. Right? So I got a 3 to the n canceling out with a 3 to the n down under, and I'm just left with 3 down under. 1/3, that's already a positive number, so I don't need absolute value bars anymore. Okay? And then here's a x plus 2 to the n plus 1 and x plus 2 to the n. Okay? X plus 2 to the n plus 1, that's the same as x plus 2 to the n, which I can cancel with the one down there, and then times x plus 2. I need to keep the absolute value bars around the x plus 2 because I don't know anything about x here. And then times n divided by n plus 1 times the ln of n plus 1 divided by the ln of n. Okay, so that's what I got so far. And I can lose the absolute value bars around these n terms because n is a positive number anyway. Let me find the limit as n approaches infinity of the ln of n plus 1 divided by the ln of n. You're going to use L'Hopital's rule to begin. Okay, so that's the limit as n approaches infinity of 1 divided by n plus 1 divided by 1 over n. So derivative of the top divided by the derivative of the bottom. When I flip the denominator, I'll have n divided by n plus 1. I can use L'Hopital's rule again. And derivative of the top divided by the derivative of the bottom. So I'll have the limit as n approaches infinity of 1. That's 1. Okay? So I end up getting 1 there. And by the way, the limit as n approaches infinity of n divided by n plus 1, right? That's 1 also. Right? We already found that. Okay? So I just need to know when 1/3 times the absolute value of x plus 2 is less than 1 to know when this series is going to be absolutely convergent. Okay, if we multiply both sides of this inequality by 3, and then use the definition for removing the absolute value bars, x plus 2 is between -3 and +3. When I subtract 2 from -3, I get -5. And when I subtract 2 from 3, I get 1. So x is a number between 1 and -5. So far, all those numbers are going to make this series converge. Okay, now I got to check the endpoints. So check the left endpoint there. When x is -5, let's see, I got -5 plus 2, that's -3 to the n, divided by 3 to the n. That's -1 to the n. Okay, times the ln of n divided by n. And with that -1 to the n term that I see, that's kind of a giveaway to use the alternating series test. Okay, so the limit as n approaches infinity of the ln of n divided by n using L'Hopital's rule, that'd be the limit as n approaches infinity of 1 over n divided by 1. That's 0. Okay, so condition 1 is satisfied there with the alternating series test. Now, the second condition is that I have to show that the terms decrease. Okay, well, it's not immediately clear that the terms decrease because the top is growing and the bottom is growing. So how do you know that the terms decrease, right? Okay, we're going to use the first derivative test with that. So if I let f of x be the ln of x divided by x, then the derivative, f prime of x, that'd be using the quotient rule. Bottom is x times the derivative of the top is 1 over x, so I get 1 there, minus the top is the ln of x, divided by the denominator squared. Okay, so when is this a negative? Well, the denominator is always going to be positive. So this is going to be a negative when 1 minus the ln of x is less than 0, or ln of x is greater than 1. If I take e of both sides, e to the ln of x is x, and then on the other side, e to the first power is e. So anything that's bigger than e means that you're going to have a decreasing function on the interval e to infinity. Okay? So the terms don't decrease right away. We're starting at 2. But they pretty much decrease very quickly after that. Okay? N is a whole number, right? So I'm going to say that the terms decrease when n is greater than or equal to 3. Okay? And so I'm going to be including the left endpoint there. Now I got to check the right endpoint. If x is 1, and we plug that in to this guy, 1 plus 2 is 3. 3 to the n divided by 3 to the n, those are gone. And I have the summation as n equals 2 to infinity of the ln of n divided by n. Okay? Now, you got a couple of options with this one. So you could use the integral test if you want. Or if we get a little creative with it, I'm using a comparison test. So the reason is because the ln of e is 1. And anything bigger than e means I'm going to be bigger than 1. Okay, I'm dividing both sides by n. So I got the ln of n over n. That's going to be always bigger than 1 over n for when n is bigger than e. Well, the summation as n equals 2 to infinity of 1 over n, that's the harmonic series, right? And I know that diverges. So anything bigger than that is also going to diverge. Okay, we're using the comparison test there. So the radius will be 3. I got an interval length of 6. And I'd get the radius back right back here, you know, if I wanted. But the interval then, so I'm including the left endpoint, but not the right endpoint. So we're going from -5 to 1. We're including -5 there. Okay. Be sure to look at the homework. This is definitely important. Okay. Definitely important for success in the next 2 sections also. Okay. All right. So we got 11.9 next. We'll go ahead and stop the video right here, and I'll start in on 11.9 next.